Hello again, everyone. Welcome to part 2 of the lecture covering mechanical properties of materials. In this part, we're going to continue with describing a few more mechanical properties that are driven by inelastic behavior of materials. If you recall, a material property is something that is independent of amount. We talked about different forms of deformation as dictated by the response of materials to stresses, quantified by strain. We also described some linear elastic properties, Poisson's ratio, and the modulus of elasticity. The boundary for their applicability in terms of deformation was up to the point where deformation becomes nonlinear, denoted by this black dot. Up to this point, the material will recover all strain imparted once the stress is removed. After this point, permanent plastic deformation will occur. That will be the main topic of this part of the lecture. What happens beyond the yield stress? And what is the ultimate tensile stress? And what is toughness? Thus far, I've only displayed stress-strain curves which extend to some finite value of plastic strain. If one were to impart as much strain as one could, or load the material until it broke, you would end up with a curve that looks like this. The material is loaded elastically to some point where it starts to behave non-linearly. It would deform plastically until a peak amount of stress is achieved, and then deform non-uniformly until the final point of fracture. The sequence of events are shown here by each of the arrows. These particular intervals are characteristic of stress-strain curves, and the following properties can be obtained. The modulus, as described during the last lecture, the yield stress as the point where plastic effects are apparent, and the ultimate tensile stress, which is the highest stress achieved during the test. Note that the final point doesn't have a property attached to it per se, but denotes the end of the test. I'll explain why in a minute. Instead, let's first look at how to ascertain a yield stress. On the left, you can see a stress-strain curve where a yield point is pretty apparent. This type of behavior is very rare. Usually there isn't an obvious demarcation between linear and nonlinear behavior, as shown in the curve on the right. However, as engineers, we need to either define a phenomena or decide on a protocol for identifying this very important material property. It is therefore by convention that the yield stress is determined. Taking an experimental stress-strain curve is determined in 2 steps. First, the modulus is found if it isn't already known in step 1. In step 2, a proof stress is determined by placing a line parallel to the linear portion of the stress-strain curve, that is, having the same slope and therefore modulus, and this is offset by a 0.002 strain, if it's expressed as a ratio, or 0.2% if it's expressed as a percentage. Then the intersection of this line with the stress-strain curve decides a proof stress. There is no physical basis for the 0.2% offset value, merely convention, and with it a reasonable approximation of the yield stress can be determined regardless the shape of the stress-strain curve. Therefore, this proof stress is employed as the yield stress for many engineering applications. Now, let's consider a coupon or a specimen which is loaded multiple times. If we take a tensile loading sequence from earlier, it will appear this way. Plastically deform once passing the yield point denoted by sigma y1, and then if the stress is released, it will elastically unload, imparting a permanent plastic deformation. What if we were to load it again, further into the plastic region? Well, it would load again, elastically at the same rate, but yield at a higher stress value, sigma y2, as opposed to sigma y1. If we were to load it once more plastic strain would be accumulated, and it would yield at sigma y3, approximately at the same magnitude of plastic stress where it last left off. If the deformation were to continue, the stress would carry on increasing slightly to the point of ultimate tensile strength. The ultimate tensile strength is the point where ductility is exhausted, that is, no more plastic strain can be uniformly developed. In a tensile test, this is the point where non-uniform deformation occurs, a phenomena called necking. This phenomena has one area locally dilate far more rapidly than the surrounding region and it will appear on an engineering stress-strain curve as a gradual decrease in stress prior to final fracture. The value of strain at which the UTS occurs is a measure of the specimen's ductility, which is a concept we'll discuss next. Consider the stress-strain curve on the left versus the right. The specimen on the left can be considered brittle, as it accumulates very little strain before the ultimate tensile stress and fracture. The curve on the right is more indicative of a ductile material. There is an appreciable amount of strain prior to the ultimate tensile stress, and afterwards, more strain can accumulate while it undergoes necking. This is shown by the fracture surfaces of the specimens themselves. There is little to no evidence of a neck on the left versus a very well-defined neck on the right. Sometimes you may come across material data which quantifies the strain to failure as a measure of ductility. However, this is a bit of a caveat because it requires weighing against the size of the specimen employed, and it can vary from specimen to specimen. And this is what I was referring to earlier. A better comparison of ductility between two material types would be to employ identical specimen configurations. Then it would be correct to say that the one which demonstrated a higher strain to failure would be more ductile. Following on from ductility is the concept of toughness. Here we have a brittle material behavior shown in blue, while a considerably more ductile material is shown in red. The definition of toughness is the amount of energy absorbed during a deformation event per unit volume. Recalling that stress is a measure of force over an area with a base SI unit of a Pascal, and that the base SI unit of force is a Newton, and that the base SI unit of energy is a joule, and also recognizing that the strain is unitless, as it is a ratio of lengths, then an expression for the overall energy absorbed during a deformation event is the area underneath the stress-strain curve multiplied by the volume. If we compare the areas under each curve by inspection, it is clear that more ductile material has a far higher toughness than the brittle, even if the other properties are greater. For example, both the modulus and yield strength are higher for the brittle material rather than the ductile. The toughness is dominated by the amount of plastic deformation that can occur. Indeed, for metallic materials, if a higher toughness, and by virtue ductility, is imparted by some form of processing, then this will be at the expense of strength. So that's it for part 2. We have covered basic mechanical properties of engineering materials. We've also discussed a key testing technique to ascertain these properties. Moving forward, we'll look at what decides these properties and what trade-offs need to be made to achieve elevated properties. This information is valuable as it will enable you to ascertain what's possible when specifying materials. Until next time.